Yeah. So let's actually, I mean, I assume some of you have gone through this at some point, right? I mean, this is on the syllabus page, right? This additional details. So this tells you how much effort to put in. Like here, it's basically saying at most 8 pages. You want to. So you've seen some. I think when we're talking about, for example, using CNNs for sentiment analysis, for example, there was a short paper that we saw, right? So, for example, um, yeah, I'm not saying you have to do this, but this is a good, like example of, some title. What is your project about? And usual the way you kind of lay out your problem is what is the problem you're solving, um, and sometimes you directly get to model, but the model just means like what is the technical part of your problem that you're looking at, and some, of course, you try to use as many diagrams as possible, even if you can draw them in PowerPoint if you want, just to kind of illustrate what are the moving parts, what are the parts where you're contributing to, things like that. And that's it. And here this person goes into regularization and stuff like that in the model section, and that's it. And then, for example, you can directly jump to, now that I have this technical setup where I have a, so introduction. Typically, you can have introduction, problem, your solution, and your experiments to support your solution. That's what you do. But here it's introduction, model, experiments.
This looks like it's probably written in LaTeX. Is that a requirement?
No, it's not. It's
Okay.
not. It's not. LaTeX is easy, relatively. Okay. Of course, if you are studying it for the first time now, then maybe not. But there are actually, I don't know if you've heard of this service called Overleaf. I think I might have given a link to that, if not. So yes, for example, even these instructions are written in in LaTeX, and yeah, and and notes in 575, for example, were written in LaTeX. Um, it's okay. I mean, you don't have to use LaTeX. You can use even Markdown if you want. It's fine. From Markdown, you convert it to a nicely formatted PDF. That's good enough. What is it? It doesn't say two columns, so you can just use you can just use the same way. I mean, you can use a Google Doc. Yeah. I mean, your issue may be that you may not be able to see the mathematical symbols probably. As long as you can write the symbols in a, they should not be jarred, or like they should not become a mess if they are being used. If you're not using it, that's fine. Yeah, you can use a Jupyter notebook. You can use a Jupyter notebook, but you want to have like export it to like a PDF. Like with the once you run each cell, there'll be some plots or some numbers. At least export it to a PDF. And as Jupyter Notebook also supports cells where you can have only text, right? Markdown cells. You can have your description there itself if you want. Yeah, if you want to use LaTeX, it doesn't have to be like in PowerPoint. You can use symbols to actually and take some screenshots and all that. So there's a lot of okay, okay. Yeah. Use Don't think of this as a hurdle, right? I mean, basically, this is just a guideline to not be writing like a lot of pages or and so on. So if in doubt, just look at this. It doesn't have to double column, but at least like the way this guy is like quickly, this author is very quickly showing what's the problem, what's the model, what how is my performance on my experiments. It's a good example to see. Okay, it's in the text. It's in this part, text and embeddings lecture. This first link. Okay.
And then a 15-minute video recorded of us.
Yeah, you can just do a walkthrough of your IPython notebook if you want, or the document, whichever you want. Or it could be, if you have a local Flask server running, then you can even. I mean, you just need a screencasting software. So there's something called Open Broadcast Studio you can use. Okay, I can use QuickTime if you want on Mac to screencast. Any other questions about this? Okay, so if not, project instructions good. Um, Assignment 4 we spoke about. So okay, let's then jump into today's lecture. So today we're going to look at kind of not so much about the first point, but first point is just saying what is inference. Okay, inference we have seen, after looking at so much material over this course, we know what inference is. Inference is just nothing but computing a conditional probability or computing a marginal probability. Okay, and we'll see these examples throughout. The most important delta would be two techniques to answer the same question. But before that, there'll be this notion of a factor graph. Okay, factor graph is like, oh, last time we saw two different ways. One is directed graphs and one is undirected graphs to represent the same conditional independence metadata information, right? So instead of two different graphs for the computational purpose, we could use the notion of a factor graph. Okay, that's the second goal. So to understand what is a factor graph, that's going to be not too difficult. Um, and then to do the inference, there are two types of techniques you can use. One is called belief propagation. Belief propagation is a name, but ultimately all it's doing is your usual. When you're doing marginalization, for example, you kind of do summation over the variables which you don't care about, right? Belief propagation is all about how to do those summations very efficiently or very in a computationally efficient manner. And the second technique to do compute conditional probabilities, marginal probabilities, and other things is sampling. Okay, and we're going to revisit Gibbs sampling. So we've already seen Gibbs sampling, and some of you have seen it in 575. So we'll revisit Gibbs sampling and a little bit more details on that. Okay. So as the goal is clear, what is inference? What is the factor graph? What is belief propagation? What is Gibbs sampling? Okay, four things. So So let me jump to where we are. So we are last time we spoke about conditional independences. Okay, so these are the most important, metadata information that we're capturing, and basically we saw several graphs, right? LDA, one for LDA, one for Bayesian linear regression, hidden Markov models. They all capture some sort of conditional independences. That's what the graph captures. Okay, and that's what we saw last time. So this time we're going to look at inference, and we'll see how conditional independence or the graph structure helps us, solve the inference problem. Okay, and as I said, the back of your mind, you should think of just marginalizing or computing conditional probabilities as inference problems. And next time we'll look at learning. Okay, learning the parameters of such models. Okay, like um, that's where you go back to maximum likelihood estimation or variations like that to learn the parameters of the distribution. So remember, in this whole three lecture series, all you're saying is we have a distribution. We just want to have metadata that's captured by a graph. And so, given a distribution, what all things can you do? You can compute expectations, you can compute marginal probabilities, you can compute conditional probabilities. So that's what we're doing. So there's not much anything complicated going on, but there's a rich enough language to capture many of the models that you've seen so far. Not the deep learning models, but linear models, linear regression, LDA, and many Gaussian mixture models and things like that. So let's start with the notion of a factor graph, and then we'll look at what are the two ways to inference. Not these are not the only two ways, but uh, um, we'll look at what factor graph is first. Okay. So before that, what is inference? Let's be concrete. So let's say we have a D or a p-dimensional random vector, and it belongs to some domain, and each coordinate has some support. Okay, which just means that let's say some coordinates are continuous, some coordinates are discrete. Then that's all it's saying, that this is the domain of the values that the random variable xi can take. And P is a distribution over these d-dimensional random vector. Okay, and inference is all about just computing functions of it. For example, here is an example. So you want to compute the mode of this distribution. So our operating object is always a distribution. You just want to compute things on it. So mode would be find the point which maximizes the density function. Okay, in this case. Or the mean is just the average. For example, if they are, let's say they are all discrete random variables, then you just average over all assignments of the values that x can take. Okay, and let's stop this. So a marginal distribution is just some. Let's say you want to find a marginal over xi, then you sum over all the variables you don't care about. Okay, that's what a marginal distribution is. Okay, and a conditional distribution is, of course, again condition on everything else. What's the probability of, let's say, your random variable of interest? Okay, so these are inference problems. Okay, here we are not learning any parameters. The parameters of the joint distribution, the distribution of which is already given. You just want to compute some functions like this, sum out all the other variables or compute this. You may say, oh, these seems to be things which we already know how to do, right? Like summing out, this is literally sum out other variables, okay? But the point is, how do you do this efficiently when you have lots of random variables and there's a graph related to that, okay? If you just have like 2 3 random variables, you know how to sum out. But if you have a lot more, then it's not clear how to do it very nicely, okay? So that's inference, and we'll look at basically some simple, very intuitive techniques to do inference. I mean, in fact, variable elimination, you have to eliminate variables that you don't care about. For example, if you're marginalizing, so that will give us a sense for, okay, variable elimination can sometimes be slow, so let's look at a more sophisticated algorithm, that's Bayes propagation, and there are also some approximate techniques which are sampling based. Okay, so we'll get to these three techniques one by one, increasing, I would say not increasing complexity, but first one is just a variable elimination is like simple, and then Bayes propagation and Gibbs sampling are going to be very interesting. Two different but techniques to do the same task. But before that, let's talk about factor graphs. Okay, factor graphs are basically a way to disambiguate, like way to understand just from the graph what the how are the variables related to each other. Okay, so by which I mean, like if you look at this graph, this is an undirected graph, just three nodes, right, A, B, and C. The problem is by just looking at this graph, I cannot tell you what the factors are. In the sense of there's an ambiguity. I can either, because this is a clique, right? I can say there's only one factor, which is P, A, B, and C. Okay, so the joint distribution between A, B, and C is just has one factor. Or I can say, oh, it's a clique. It's actually a collection of three cliques. These three, each edge is a clique, by the way. So there'll be three factors. Phi1 of AB, P2 of BC, P3 of CA. Okay. So look, remember the graph is supposed to tell you something about the factorization. So by just drawing this graph, you're not able to tell what the factorization is. There could be multiple factorizations. Okay. So to address that, there's a very simple idea, which is as follows. If you have this original graph, what you do is you also, let's say you also know the factorization. Okay, this is the factorization you want to encode. So you know that there's only one factor. So what you do is for each factor, you introduce a square node. Okay. So first of all, you drop edges between the variables. So these three edges you drop. Okay, and you look at the definition of the density function or the distribution function here, the probability mass function. Sorry, and it only has one factor, phi of a comma b comma c. So for one factor, I'll have one square, and then I'll just connect it to the three variables that are its arguments. Okay, so a, b, and c. Therefore, there'll be three edges to the three nodes. Okay, so what are we doing? Variables. So previously it was a graph of just variables, but now what we did is drop all the edges between the variables, and wherever there are factors, if there are like three factors, then there'll be three squares, and squares will be connected to variables, okay, whichever variables they're related to. And so we'll see an example. In the next slide. Okay, factor graphs. So the name of this graph here is called a factor graph, and it's just supposed to capture the factorization of the graph for a function. As I said, if it's a product of factors like this, then the graph will have a square node for each factor and a circular variable node for each variable. So that was variable nodes were there before. It's just that the square nodes are new. And so why do we need this? It's just a way to kind of know what are the factors. Okay, especially in undirected probabilistic graphical models, you wouldn't know what the factors are by just looking at the graph. But at least directed graphical models, you know what the factors are. So that's just a way to disambiguate this issue. Okay, so here's an example. If this is the Markov network, or basically the undirected graph, then here are two examples. In one factor graph, there's only one factor, phi of A, B, C, and D. In the second, in this example, there is one factor for each edge. Okay, 1, 2, 3, 4, 5, 6. Okay, so six squares for one for each. So if I draw this, so these are factor graphs. This is just the original undirected probabilistic graphical model. This side is the factor graphs, and if you draw the factor graphs, I know exactly what the factorization of the joint distribution is. No, they are equivalent in the sense of no. So they just tell you what the no, they're not equivalent in the sense that in this case I only know that the joint distribution is just the joint distribution. So there's not much information going on. Here it says that the joint distribution factorizes into many products. Okay. So we'll did I write it? No. So here I think we saw the example, right? So knowing this uh, is information. Okay. So knowing that things factorize this way is useful information. It's just a it's information that is not if you just draw the undirected probabilistic graphical model, you wouldn't know whether the factorization is over the smaller cliques or the bigger cliques. Okay, like an edge is a clique itself. Okay, so you wouldn't know if the joint distribution had a factor which was just a function of the like you wouldn't know by just looking at this graph whether the joint distribution between A, B, C, and D has a factor like this or a factor which are like six of the factors like this. That's all. So the factor graph is just saying, oh, previously I knew something about conditional independences, okay, that I can talk about here. But now I'm also going to tell you what were the factors in the joint distribution. Okay, at least whether it had six factors or whether it has one factor. That's all it's kind of saying. Not much, nothing more. So here's an example. So you have a graph, and if you ask like what is the distribution that it corresponds to, okay. So you can see first of all that the variable nodes are not connected to each other. Okay, there's no edge between the variable nodes. Okay, there's no edge between the factor nodes. But each factor node will be connected to a bunch of variable nodes. Okay, and what is the density function here? Probability of x1, x2, x3 is by just looking at this graph, I can say, oh, there's four factors. One by let's say one by z, fa of x1, x2 times fb of x1, x2 times fc of x2, x3 times fd of x3. Okay.
You might have said this last class. What is the 1 over z here? It's some sort of
It's just a normalization because these functions are just supposed to be positive. I mean, but this thing is a probability density function or probability mass function, so it has to sum to 1. So z is just summing of the numerator over all assignments of its inputs. So z is called a partition function. It's a very interesting object, and in fact, there are so many papers written on it, how to compute it. But so I think I just wrote that in the next slide. Okay, so you don't have to write it. This is the by looking at the graph, you can just look at this is the factorization. Okay, because there are four factors, so four square boxes, so four terms, and each square box is whatever it's connected to is its arguments. Okay, that's a factor graph. And why do we need this factor graph representation? It's going to be useful for variable elimination and Willy propagation ideas. Okay. Okay. So here is another example. So here I've mixed the notation a little bit. So let's call this probabilities. Okay, maybe. Okay. Then you can just see that probability of x1, x2, x3 is probability of x3 given x1, x2, and probability of x1 and probability of x2. So this is a specific information about a directed probabilistic graphical model, right? But given this factorization, if there were probabilities, then z would be just 1. Okay, and if that's the case, then this is the following graph. This is the graph where we know that one factor has to connect to three of them. So there is one guy which is connected to all three variables, and there's one which is just connected to one variable, another square node which is connected to another variable. So that's these two guys. So this is the factor graph. So I'm just in the past couple of slides, I'm just motivating what a factor graph looks like. Okay, something like this. You just need a node for a square node for a function in that joint distribution expression, and the variables themselves. If there are three variables, there will be three circles, and if there are three functions in that factorization, then there is three square nodes like this.
For now,
Yeah.
do factors just represent some sort of function acting on a distribution?
Factors are just in general, factors are just functions, positive functions. That's all. They're not acting on distributions. They are just given three arguments. Like if this one takes some value, this one takes some value, this one takes some value, they just have to evaluate to some positive number, non-negative number. Sorry.
Okay.
Yeah, that's all.
So
Factors are just they're not by themselves related to they're not by themselves any probability density function or mass function, but their product is equal to a probability, let's say, mass function. But of course, their product can be arbitrary number, so that's why 1 by z is just scaling them down so that they are actually going to be uh, corresponding to a probability mass function. So they're just arbitrary functions. I think we saw an example from last time. Maybe I can open that.
but it's not something like an activation function, like a neural network or something like that.
No, these are very simple functions. So in fact, let me just show you that example. Yeah, you had a question.
Yeah, but I wanted to. It was on that last slide. It was related to the background.
Let me just show you what the. So I think towards the end of last. So let me just finish up at the start. So here is an example, right? So what are factors? If there was a three node graph like this, and if somebody told you that the distribution between A, B, and C factorizes into three factors, okay? These are three factors or three functions, and each one is just a function. So it's a function of two arguments, and each argument takes just two values. So that's why I can represent it as a matrix. Okay. I mean, even if it takes more values, I can represent it as a matrix because there are only two arguments. Okay. And these are the numbers. This is what the function value is to. If A is 0, B is 0, it's 10. Of course, this number 10, is not like a probability value, right? Because probabilities have to be between 0 and 1. So Z is something which says, oh, the denominator should be like some sort of normalization constant, such that the whole thing is, this thing is a probability mass function. So that's what a factor is. Yeah, you had a question?
Yeah, it was on this slide. So I can see how you can get the graph from the equation.
Yeah.
But
you can go both ways.
So
Oh, you can't get to this though. I mean, this perpendicular stuff was because of.
That was my question.
Yeah,
so the x3 given x1 and x2.
Yeah, you wouldn't get this. Yeah, you wouldn't get this. So you
could
would.
be anything.
Yeah, that's.
Any relationship. It would just have to have the three variables.
Yeah, it would just be three variables. Yeah, you wouldn't know.
Ask you if it could be x1 given x2, x3, x.
Yeah, so let's not do that. Okay, so that information is not here, so we don't know. Okay. So that's why I said in the previous slide, let's call this probabilities, because then it is clear. Right? Probability of x3 given x1, x2. But still, once you draw the graph, you wouldn't know what conditioning is.
But
Yeah.
from the formula, you could draw the graph.
Yeah, from the formula you can draw the graph, of course. Yeah, so we don't. So for that, okay, factor graphs actually are more relevant for undirected graphs, because directed graphs we already know, like there's going to be one factor for each variable we know. So if there are like 5 random variables, then we know that there are going to be 5 terms. There has to be a probability of that variable given its parents, right? We saw that directed probability graphical model expression. So we don't really need. I mean, the factor graph representation is kind of simple in the sense, if there are 3 variables, then there has to be 3 square nodes. One per like matches with one variable. Okay. So anyway, so that's factor graphs. So now let's go to inference. Okay, start with a simple inference idea, and then kind of extend it to more complicated graphs. So we're going to do variable elimination. Okay, and it's a name. It's a mouthful, but all it just means is that basically how to eliminate variables. Okay, so the idea is that if you have let's say you have a yeah, actually there are examples, so I don't want to write it. I don't want to do another example. So what is the variable elimination idea? So basically it's about doing sums in a clever way, or at least doing sums on um, some of the variables first. Okay, so okay, let me tell you the idea through an example. So let's say this is a factor graph. Okay, we don't really need whether did it come from an undirected probabilistic graphical model or a directed probabilistic graphical model is not important. Okay, this is the factor graph. So you can see that there's 1, 2, 3, 4 factors, and there are 4 random variables. Okay, and let's say, I mean, looking at this factor graph, we know what the factorization should be. It's f1, which involves a and b, f2 involves b and c, f3 involves c and d, and f4 just involves d. Okay, and let's say we want to do this marginalization. So we had this joint distribution which factorizes this way, and now we care about finding p of a comma b. Without knowing anything about the rest of the lecture, you can say, oh, I just need to find this. I know this factorization. Okay, I just need to average out C and D. Right? If I average out C and D, then I'll get P of A comma B. Right? That's marginalization. Right? But okay, so let's start with marginalizing out D first. Okay, so marginalizing out D is actually a variable elimination step. Okay, so we just randomly chose D. We could have chosen C first, but let's choose D first and then eliminate that variable D. Okay. So probability of A, B, and C is just sum over D of the joint distribution between A, B, C, and D. Right. Now that we can. So what is P of A, B, and C, A, B, C, and D? We know what it is. So that's this term here. Okay. Now what we can see is that sum over D, because of this factorization, the sum over D can be pushed inside because these sums have nothing to do with D. Okay, right? These sums have nothing to do with D, so I'll push it inside till I only retain terms which involve D. Okay, so those are the two terms. So okay, so those are the two terms. So I'm just gonna use a shortcut. Don't I think it's not very important to remember this particular shortcut. All it's saying is, oh, I'm summing over D. What is the variable left? There's only variable left C left, so that I'm just going to call this a function of C. Okay. See, if I sum over D is a running variable here, so we'll drop it. But the remaining whatever term I get, it depends on C. Right? For every value of C, it's going to be a different term, different number. So that's all we're calling it as a function of C. Okay? And so we can replace the summation with something like this. Okay? It's just a function of C for now. Okay? So that's so once we have this function of C, all I'm trying to say is that there's A, B, B, C, and some function of C. So we have eliminated D. Okay, that's variable elimination. Very simple idea. And now we can do another variable elimination, which is eliminating C. So P of A comma B is of course summation over C of the joint distribution between A, B, and C. Right? You can sum out C. Now summing out C is again you kind of try to see whether the summation of C, the first term doesn't involve C, so that you can just retain as is, and then the second term involves C, and we said this whole thing, let's call it a function of C. So that's over here. Okay. So the function of C is here, and then the remaining function of C is here, and C is a running variable. So I'm going to sum it over. The term which remains is a function of B. I'm just calling it as some function of B. So it's basically the way to if you want to care about remembering this shortcut is just saying that, oh, I'm going to sum it over B, and the remaining part is just a function of B. That's what it means. Okay. It's not a big deal, so don't worry about this shortcuts. But all I'm saying is you eliminated D, you got a function of C. Now whatever involves C, you sum it out. Whatever is left is a function of B. Okay, so that's the that answers your original question of finding probability of A comma B. Okay, very simple idea, variable elimination. Any questions about this? Okay, so now why I'm going to go forward. I mean, so this seems like why do you even introduce this? Is that I started with a summation of D and then did a summation of C. You could do the opposite as well. And a priori, it's not clear what summations you should do first. For example, summation of D involves some matrix, basically like a two-term function and a one-term function. Here also it involves a two-term function and a one-term function. If you had done the summation of C first and then D first, then maybe it would involve some other sums and products. Yeah.
Like a term 1 by a.
D over there, and then it was.
Here.
I'm just trying to figure out like when we did the computer for all C, the first blue box.
Yeah.
We would have to make sure we had all the terms with D in there, right?
Yes.
So if there were more terms, we would switch them
Yes.
over. What would have happened if there were A's or D's at switch?
Oh, here A. Then this would be a function of. I mean, this would be some complicated. Some function of C and A, for example. If this had F3 had a connection to A as well, then you would have to. I mean, then this function here would be function of C and A, right? It's just you're eliminating D, so that whatever remains is going to be for each C and A. Maybe you eliminate D.
Would we still want to use this method if we did have an extra linkage like that, or would
Yeah, so right now there's not much method going on here. We just wanted to, so we have a joint distribution, it factorizes in some way. We care about some marginal probability, maybe marginalized or only on two variables. And obviously the thing you need to do is sum out the variables that you don't care about. Okay, here in this example, we are just saying, oh, what if we sum over D and then what if we sum over C? This is how you would do it, okay, computationally. The point we need to take from here is that sometimes, so it's not, so the summations because of the factorization can be pushed inwards. If you did not have this factorization, then there would be like a huge table of every assignment to A, B, C, and D, and then some probability, and then you have to pick up the rows to do the summation. Okay, that's basically how you do it. Because of the factorization, you can push the summations inside, as in like a few, like you're being a little bit efficient here. Okay. Right. For example, let's say D takes two values, then this involves only sum of a product here and then sum over two values. Okay. But let's say if let's say A, B, C, and D took two values each, and there was no factorization like this, then to drop out D, you would have to look at I think several eight rows. Yeah, you need to look at 8 rows. Did you understand what I said? So okay, let me actually maybe I mean the ideas are very simple. So whatever, some color. So all I'm saying is so 0 0 0 0 0 0 0 1 whatever 0 1 all the way to 1 1 1 1. Okay. 0 0 1 0 0 0 1 1 and so on. So there are going to be 16 such rows. Okay, with 16 such rows of all the assignments to A, B, C, and D. Okay. So these are all the values that random variable A, random variable B, random variable C, and random variable D take. Now to marginalize out D, if you did not know the factorization, okay, that means that for every assignment there will be some number. Okay, that's the probability of that assignment. Okay, so you'll have to for D to sum over D. Then you have to fix. Okay, let me fix in this case A, B, and C. Okay, A, B, and C will be some value 0 0 0. Then there will be I think. Yeah, you can see that there are 2 rows for which you need to sum, but there'll also be for each A, B, and C assignment, you will have to sum over 2 rows basically. So you will basically compress. If you marginalize over D, then you will have a 8 row. Sorry. 8 rows where it will be 0 0 0 0 1 0 0 1 0 and so on. Okay, this is what you'll get, but you'll do 8 summations. I mean 8 summations. Okay, for each assignment of A, B, and C. Whereas
So there will be two such tables, right? This table for D equal to 0 and that same table for D equal to 1.
no, D is marginalized out, so we'll add these two basically for every assignment. Basically, we're adding 2 rows for every assignment of A, B, and C. So okay, this is what you would do naively if you did not know the factorization. Okay, now if you know the factorization, your tables will be smaller. Okay, so your tables will only involve, for example, in that example, I think it's a function of C and D. and some function of d, I think. So you will have like a four row table, C and D, and then a 2 row table, 0 and 1 for D, and some number 0 0 0 1 1 0 1 1. So for this, from these two tables, you will compute for C is equal to 0 and 1, some two numbers. Okay, so this is like a much less reduced computation. So here you're just averaging for C is equal to 0, add these two, right? Two probabilities here, and for C is equal to 1, add these two, but you also have to multiply f of d. So that's what's happening um, here. Okay. Because I know the factorization, I only have to worry about like a small, much smaller tables is what I'm trying to say. Tables doesn't like it only involves this summation, okay, which is a summation over two numbers here.
So would you say that every time you marginalize a variable out,
Yeah.
you create maybe like this little mini lookup table for some value? And you say
No, because you know the factorization, you can push the summation inside. I mean, all these, if I know the factorization, each one is a lookup table, each one is a smaller table. If I did not know this factorization, it will be that 16-row table. Okay?
Okay.
That's all. So it's just this factorization is giving you smaller tables, and so you can work with smaller tables first, and then progressively like work with the next smaller table. Like whatever you get a small table here, and then each one corresponds to a small table. So these types of summations and additions take less computation. Okay. Yeah.
So if we sum up 2 digits of D,
Yeah.
so after that, do we have to sum 4 digits of C? Because
No, there is no 4 digits of C. So you get this, and then you'll use this in the next. So this is what I was calling as mu d to C of C. Okay. In that here, mu d to C of C is just a two row lookup table, okay, or not lookup table, a 2-row table. Okay. And here again, f2b comma c is again a 4-row table with a 2-row table. You just do this local computation to get another 2-row table. Okay. So things are being efficient in some sense. Okay. So if you want to do summation over d, what you're saying is that okay, fix a value c. Let's say c is 0. Then I have to take look up this value c. For c 0, d can take value 0 or 1. D takes value 0. Look up this number times this number. That's the first product. And when d is taking value 1, look up this number and this number. That's the second term. Add those two. That's the summation, right? For the given value of c is equal to 0. That's what goes here. I think this is like there's nothing deep going on here.
you see that slide just
Oops. I think okay. Okay, so what is the main idea in the past few minutes is that we have factorization because we have a factorized graph, factor graph actually, and we want to let's say compute marginals. Then we have to average things out. I mean, in a sense, irrelevant variables anyway, we have to sum them out. I just illustrated one way to do it, like let's say sum d first and sum c first for that example. That's it. That's variable elimination. You just choose some order of summing up things and you sum them out. Okay. Now, why we are going to the next idea, which is Billy propagation, is that it's not clear what is the order in which you need to sum. Okay. So let's say you had 10 variables that you are supposed to sum. Okay. To get p of a comma b, then should you sum d first and then c first and then e first and then f first? It's not clear. Okay. So that problem you can and of course the order of summation does influence the computation, how much computation you do. Okay. So that's the I guess the motivation for looking at a more interesting algorithm. Should we move forward? Okay. So belief propagation is basically a way to do variable elimination in a clever way. Okay. And it's also called the sum product algorithm. and you'll see that there's going to be summations and multiplications involved, and we already saw some in the previous example. And factor graphs which are trees is where this algorithm will compute the right answers. As in, right answers means the right marginal probability values and the right conditional probability values as needed. But if you have factor graphs which are not trees, okay, then this elimination procedure doesn't work. Okay, there are examples where it doesn't work, but it still is a very useful algorithm because it kind of removes your issue of, oh, what should I sum over first? Okay, so let's start with a more interesting graph. Okay, instead of that line graph that we had. So in this graph, again, there are 5 variables instead of 4 variables, and there are 5 factors, as you can see here. Okay, so because when looking at the graph, I know exactly how the factorization should look like. It should look like this. Okay, and now again, I want to compute the marginal of p of a comma b. Okay, and the way we're going to do this is going to be using the notion of messages and the notion of passing messages to each other. Okay, so we will understand what is a message and how is this message, like what is meant by passing this message. Okay, so message is a word being used here. Message just means for us it's going to be a vector. Okay, so let's think we are in the discrete world. So let's say all these a, b, c, d, and e are, let's say, binary for example. Then a message will be just a 2-dimensional vector. Okay, and we've already seen a message before. That the table that we saw here is essentially a message. Okay, this is what a message means, a 2-dimensional vector. But we'll get there. Yeah.
This would be either an undirected or directed because the number of functions are equal to the number.
Yeah. Yeah.
You don't know that.
Yeah, we don't know that and we don't need it. Okay, these f's could be actually probability of b, probability of d given e given d, things like that. We don't need it. Okay. So what are messages? Messages are basically vectors. So think of all these random variables as binary for simplicity. So all these vectors will be 2-dimensional. Why 2-dimensional? Because binary random variables take 2 values, 0 and 1, let's say. So for each value, we'll just have a number. Okay, so it's like a vector because there are 2 binary random variables take 2 values. For each value, we just need to compute some intermediate numbers. Okay, so that's a vector. The vector will have 2 cells, 2 numbers, and what do we do with these messages? Okay, these 2-dimensional vectors, they get passed from one node to the other. Okay. Now remember, there are 2 types of nodes. First of all, the circular nodes, which are the original variables. There's also square nodes, which are the factor nodes. Okay, so messages are going to be passed. For our example, since I said all the variables are 2-dimensional, binary valued. So all our messages will be 2-dimensional vectors. Okay, all these messages, which I'm calling as 2-dimensional vectors. Okay, what does the bracket indicate? Bracket C means that the message involves a random variable C. Okay, and here, for example, bracket D means the message involves a random variable D. Okay, so messages are always the same dimension as the random variable that they're involved with. So for our example, it's always 2-dimensional because all these random variables are 2-dimensional. Okay, and we'll see. Right now in this picture, what I want to introduce is that there are going to be messages. Okay, messages are going to look like this. Okay, look like this in the sense I'm going to use this notation. This notation looks like there's too many symbols. Okay, mu is just always a constant, always a fixed thing. The notation will involve 2 subscripts and 1 argument. Okay, and I'll explain what these 2 subscripts and argument mean. So in this picture, all I'm going to show is that there are going to be some vectors which will be passed to nodes, to another node, to another node, to another node, to another node. So that's how the computation happens here. Okay. So let's start with. So it's the same picture from the previous slide. I guess shrunk a little bit, and now I want to compute p of a comma b. That involves, of course, if I want to compute p of a comma b, I have to sum out d, e, and c, d, and e, right? So that's the summation here. Okay. So I know in this factorization, because I know the factorization from the factor graph, I know this doesn't involve c, d, and e, so I can push the summation of c, d, and e up to this point, right? And I have, of course, these all these factors remaining. Now I can, of course, at this point see, maybe this, and this doesn't involve e, so I can push e all the way here, and so on. But let's not do that. Okay, let's do the following. Whatever the summation is, okay, whatever the summation is, it's gonna, C, D, and E should not feature because they're being summed off. Okay, so the only things that this should be a function of are what? B. Okay, B is the only thing that's not being summed off. Okay, so I'm gonna use a shortcut for this huge summation here, and we're gonna decompose the summation in the next few slides. But this huge summation, only B is the only thing remaining. So of course, this summation will be for every B there will be different value. B only takes two values, so this is the message vector. Okay. Now another thing is that I'm gonna call this a message from F2 to B. Okay, from F2 to B, from this node here to B here. Okay. Why is that? Is because the summation involves everything to the right side of F2, right? Basically, F2 is connected to B and F2 is connected to some other parts. All these other parts are somehow in this summation going on here, right? Ultimately, F2 is also part of this, and then whatever is being computed here, it will be a multiplier to F1 of A comma B. Okay, so and F2 is connected to B, so that's why we are calling it as a message from F2 to B. Okay. So we'll just, in this example, we'll just call this a message from F2 to B. Okay. And we'll see a couple of more examples of messages like this. So, and in fact, this message of F2 to B, okay, is that summation which we wrote here again. And now I push the E inside. Okay. What I pushed inside, okay, this part. Okay, so let's focus on two parts. Okay, so there's a term C involving C here, and there's a term involving D and E here. Okay, if I sum out sum out E, then this thing is a function of remaining function is D, right? So I'm going to call this a message from D to F2. I'm going to call this a message from D to F2. Why is that? Is because if you go back to the graph, so here's D. D to F2 is what I'm calling this message as. It's basically saying D is connected to some other parts and also F2. Okay. Whatever these other parts were, F4 and F5 are being considered in this local computation. Okay. So since F4 and F5 are being considered, and now whatever is left is a function of D still, and that I'm thinking of it as being passed to F2. Okay.
So the message from F2 to D would be if D has value 0 and 1.
F2 to D. F2 to D. Let's not worry about F2 to D because that's a.
So if, for example, you do B of F2 arrow B.
Yeah.
So if B takes 0, 1, and if I
Yeah.
look at it in a tabular form, it will be B of 0, message.
The message value will be some value. Okay, like
0
0.3.
message, 1 message.
Yeah. Zero for 0, the message could be 0.3. For 1, the message will be.
But in a tabular model, that's how I.
Yeah. So these are just vectors. Okay. And similarly, F3 of C, we're just calling it as, although there's not really a message going on, we'll say this is a message from C to F2. Okay. Because C is connected to F3, C is connected to F2. Okay. A message from C to F2 is basically kind of somehow average out or get rid of F3. So there's nothing going on. So it's just C to F2 of C. Okay. It's again a two-dimensional vector. So actually, let me extract the pattern. So let's go back to the previous step. So message from F2 to B was the summation. This summation where I just gave some additional names here. Okay. Now this summation from F2 to B is basically involves F2. The reason why I use this notation is to say that there's a message from the other guys which were connected to F2. Okay. So the message from F2 to B involves F2 itself, the function itself, and the other variable nodes which are connected to f2. That's why. So that's why I put a red f2 here. Okay. So that's the general pattern I'm trying to extract. Okay. So let me actually write a general pattern here. Maybe I'm not explaining it well. So this is the same thing, same equation from the last slide. Okay. The message from f2 to b, we just said it's whatever was the local function, the function f2 itself, and messages from the other variables that were connected to f2. What were the other variables? C and D. That you can see, C and D. And I just use the short form. Remember from the previous slide, whatever the functions were, I just call these short forms, right? Remember? So you can see that the message from f2 to b involves f2 itself and messages from other guys connected to f2, okay? So which is this guy and this guy. Okay. So that's the pattern, or in general, the message from a factor node to a variable node. Okay, think of x as b, for example. This is f2. The message from factor node to a variable node is going to be a summation over all the nodes other than the target node, in this case b. Okay, so of the factor f2. So f2 is a function of b, c, and d. I want to send a message to b, so I'm not going to do a summation over b. I will do a summation over everything else other than b. That's what this is. Of the local factor, which is f2, and all the messages, incoming messages from other nodes, okay, of this factor node, but not the target node. Okay, so this factor node f2 was connected to b, c, and d, and so I want to take messages from c and d, multiply them with the local function, average out c and d, and the only thing remaining is b. That's what I'm going to call as a message from f2 to b. Okay.
That is just the function f2 and mu c and mu d are subscripts, right? That's
Mu. So this is like a message from a variable node to this f2, which is the factor node. Okay. So these are. I mean, so there is a. So maybe I think some of you are not following, but they have a special structure. Okay, so all these functions, for example, for us are just two-dimensional. Okay, because each of the random variables is two-dimensional. So this is like saying, what is this function for b is equal to 1? What is the function for b is equal to 0? That's what this is. Okay, but these functions have subscripts. Okay, the first subscript is saying from message from whom, and the second subscript is saying the message to whom. Okay, to from and to, basically. This is a message from the factor node f2 to the variable node b, and I can only do this message because they are connected to each other. f2 is connected to b. Okay, that's why I can pass a message from f2 to b. All we are saying is the message from f2 to b involves some local summation going on. Okay, the message that I want to pass to b involves some local summation. Local summation, because I'm a factor node, I'm going to use my factor function that I have because I'm a factor node, and the messages that I get from other nodes which are not b. Okay, so because I am connected to b, c, and d, I want to send a message to b. Everything else, in this case, is c and d. So those two guys would have sent me messages. I'm going to multiply those two messages, multiply it with my local factor function, do the summation over all the variables not related to the target where I'm trying to send a message to, and then that's going to be my message that I will eventually send to the target. In this case, node b. Okay. It's a lot of interpretation going on, but the reason why we need this interpretation is that once we understand these messages, so they're like right now what we're discussing is what is a message from a factor to a variable. Okay, so this is a factor to a variable. Okay, we'll also see another type of message which is called a variable to a factor, and then given these two types of messages, we can compute marginal probabilities very nicely on any tree type of a factor graph. Okay, any tree type factor graph, because previously, remember, for let's say I give you a graph of 100 nodes, which is actually a tree. You don't know how to do the summation, right? If I tell you find the marginalization of, let's say, p of a comma b, and it's a part of like a huge factor tree, factor graph which is a tree, then you don't know how to do the summations. It could take, if you don't do the summations properly, then you may take maybe recomputing summations or doing the summations incorrectly. Okay, because the summations involve like lots of products of terms sometimes. So that's what we're doing. Okay. Any questions at this point? Okay, so let's move forward. So the next, what I'm going to do describe is the message from a variable node to a factor node, and this message is going to be simpler. Okay, so I'm going to isolate the message that we had before. So we had a message from D to F2. Okay, so we're going to focus on this. Okay, the message from D to F2 was part of the previous computation, the previous slide. So let's focus on message from D to F2. So I want to pass message to this guy. This is the factor node, but I'm also connected to two other factor nodes. Okay, so the way I'm going to do it is, oh, I want to send a message to this guy. In this case, the way I'm going to interpret it as, give me whatever messages these two other factor nodes give me, multiply them together, and that's going to be my message that I'm sending to this target factor node. So if I want to send a message to factor node F2, okay, if I want to send a message to target, factor node F2, I'm gonna do a product of the messages that I get from the other factor nodes that I'm connected to. Okay, so D is connected to factor node F5, and D is also connected to factor node F4. Whatever messages those guys send me, okay, and these guys will send me messages which will be exactly D dimensional, so which will exactly be the same length as whatever values, number of values I'm taking. Okay, I'll just take a product of those two, and that's my new message. Okay, so the message that I send to F2 is the messages that I get from F5 and F4 multiplied element wise. Okay, so this is a simpler message. So it's just saying whatever I get, some input, some messages, multiply them together element wise, forward it to the guy F2. So message from this guy, message from this guy, forward it to F2.
So is it fair to say variable to factor you multiply, and
Yeah.
factor to variable you add, or like
Yeah, you add, but you also multiply and add. Okay, so that we saw here. You have to multiply the incoming messages and then do the addition.
okay?
Okay, so there's a little bit more complication going on with factor to variable, but variable to factor is just multiply and push it forward. That's your message. Okay, in fact, yeah. So this is a general form again, just like before. The message from D to F2 is just a product of all the factors that I'm connected to, other than the factor I care about sending a message to, and product of all the messages from these factors. Okay. So this is like saying I want to send a message to F2 factor node. I'll take a message from F5 and F4, multiply them together. That's this product, and that's my new message. Okay. So these are the two parts. Yeah.
Mu F4 to D, won't it also include mu of E to F4?
Yeah, that's like recursive thing, right? So let's think locally. So let's think locally, right? So I'm D. I want to pass a message to F2. Okay. Who am I connected to? I'm only connected to F5 and F4. As long as these guys send me some messages, I'll just pass it, multiply and pass it. Okay. Think of it locally here as well for F2. I want to send a message to B. I'm connected to C and D. So whatever messages they send me, there'll be two vectors. They'll send me two vectors. I'm gonna multiply them together, do some summation, and then pass it forward. Okay. So that's locally. So so of course you're right that message from F4 to D involves something to do with E, and we'll see that. Okay. And I think we've already seen that. I think we've already seen that somewhere, right? Yeah. Yeah, message from F4 to D does involve. So, okay. So how? Okay, what is the message from F4 to D? It's a message from a factor node to a variable node. Okay. The way to do it is there's some factor. In fact, let me do it explicitly on this. Okay, I want to send a message from F4 to D, right? Which is D. That's the message. Now, I know F4 was this. It was connected to E, and there was a D here. I want to send a message to this guy. So the way I'm going to do it is do a summation over E. Everything else all other variable nodes that I'm connected to, except for the guy I want to send a message to, which is D here. I want to send a message to D. Everything else I'm connected to is just E. Okay. And my local function F4 of D and E times times the message. In this case, message from E to F4 of E. Okay, that's the so it's like saying I want to send a message to this guy. I am a factor node, therefore I have a factor function. Okay, over which I'm going to do a summation of everything else not related to the target that I'm trying to send a message to, times all my incoming messages. Okay, what are the incoming messages? There's only one other variable node connected to me, so there will be a message from this guy to this guy. Okay, that I'm just calling it E to F4 E. Okay, we were here, and let me skip this because we are just looking at further marginalization. So let me actually tell you the general template. Okay, this is just reinforcing what we've already just seen. Okay, and what we did in the previous, I guess, 10-15 minutes was a specific example, a specific graph, and we were calling some parts messages and thinking in terms of, messages are just vectors getting composed, getting computed based on other messages. Okay, that's what was happening. Now we'll summarize the algorithm or the procedure here and also tell you what is being computed, because I just told you messages, and in the previous example what was being computed was a marginal probability of a comma b, right? So that's what this procedure or algorithm will do. It will eventually compute marginal probabilities of things that you care about. Okay, and it has three parts. Okay, initialization, variable to factor message, and factor to variable message. Okay, so those are the three parts, and the objective is to do efficient inference, as in basically take care of this variable elimination process in a very efficient way. Okay. So let's start with initialization. So let's say there's a factor node which is not connected to anybody else except for one variable node. Okay, that can happen, right? We have seen examples where there's a factor node but it's not connected to any variable node. It's not connected to anybody else but except for one variable node. Okay, then the message from the factor node to the variable node is going to be just f of x. Okay, it's just going to be f of x, because the factor node is connected to x, therefore it's just a function of x. The factor is just f of x, right? So that's the message. If x is two-dimensional, f of x is two-dimensional. Okay, it's just two-dimensional vector. It's just saying if x is equal to something, then the factor takes a value something, and if x is 1, then the factor takes a value something. Okay, so that's it. So this solves the initialization issue, because we were saying we'll pass messages and it was all local computation. So you say, oh, but to compute an output message, I need input messages. How am I getting the input messages from? So there's a chicken and egg problem that we are trying to solve, that we are solving here. Okay. The second thing is, what if there is a variable node that's connected to a factor node? Okay? It's not connected. This variable node is not connected to anybody else except for a factor node. Okay. In that case, the message from the variable node to the factor node is just all ones. Okay. So if the variable node is two-dimensional, then it's a vector which is like 1, 1, 1, 1, 1, 2 cross 1. Okay. So this is the message. This is the initialization. If this variable node is not connected to anybody else except for one factor node. Okay. And the next few slides, I'm going to focus on what is a general template for variable to factor message and a factor to variable message. So variable to factor message is, remember, a variable node is always connected to factor nodes. Let's say I want to send a message to this guy, f of x, f factor node. And how am I going to send a message? I'm going to get some incoming messages from these other guys. Okay, all other factors that I'm connected to. In this case, 3 other factors I'm connected to. I'll get some messages. Okay, they'll all be the same dimension as my x. Okay, so if x takes 2 values, then this will all be 2-dimensional. I'll get these 3 messages, multiply them element wise, and then forward, and that's my message to this guy. Okay, that's what this symbol, or this product, symbol just means. I get, in this example, I'm getting 3 messages. Messages from f1, message from f2, message from f3, 3 vectors. Okay, something like 0.31, 0.5, 0.7, and let's say 0.2, 0.2. Then you just multiply the first three columns, first three rows. First coordinates of the three guys, and multiply the first coordinate, second coordinate of the three guys. That's the final message. Okay, that you forward pass. And so that's it. Variable to factor is very easy. You just whatever messages I got in, I send it out. Okay, and you may say, oh, where did the incoming messages come from? So there is a somewhere we have to start the messages from, right? That's where the initialization part came in. Okay, you start with the leaf nodes, where either the leaf node is a variable node or a factor node, for which we know what the initial messages should be. Either it's 1 1 or the function itself, f of x itself, f of x is equal to 0 and f of x is equal to 1. So that solves the chicken and egg problem. Okay. So factor to variable message is very similar. It's just the opposite. So factor nodes are always connected to variable nodes. So variables will send their messages. If there are three variables, y1, y2, y3, they'll send these three messages. What you do is you multiply them together. Okay. So that will be a function which is now a function of y1, y2, and y3. Now there's a local function. This factor itself has a local factor, okay, which is a function of y1, y2, y3, and x. Okay, you drop x, sum over the three things that is factor consists of, so that ultimately you get a message which is just a function of the target, x, okay? And that's what you pass to x. Okay, so this is just a general template that we've seen already. It's basically saying I have three vectors. Let's say this is 2 cross 2, 2 cross 2, 2 cross 2. Then I'll get those three vectors and multiply them together. Okay, that's this part. I'll also multiply it with the factor. Okay, and then sum over all the variables that are not relevant to the target where I'm sending the message to. If I'm sending a message to x, average out y1, y2, y3 in this case. Okay. Do you want an example for this? Yeah.
Do we have the exact value of factor? What is the value of factor? We know the value.
No, we know this function. We know this function. Every factor node, square node, is connected to a factor function. We know this function. We assume that we know this function. Right? It's like the table. I think I showed you here, right? Like this is a factor. Some table. If it's an argument, if this argument is only 2, then it's a table like this or matrix like this.
Yeah, essentially a tensor if there were three variables.
Yeah. I mean, and they should be discrete and all that, but yeah, that's known.
So that function basically says we know the proportion of each class assignment accounting for both variables.
This function, what is it saying? Yeah, it's giving it's kind of saying, oh, for these assignments, the local factors maybe is high or low. It's like these assignments are highly likely or less likely. Interpretation. Yeah.
In the product function, how do I read the y belongs to? How do I read?
Good question. So there's a lot of mathematician going on. So this basically means sum over all the elements. So script f. So okay, let me specialize what's written there for the thing below. Okay, script x f is y1, y2, y3, and x. Okay, and script x f minus x just means y1, y2, and y3. Okay, those are the three. And y belongs to that just means that take all the values that these three random variables take. Okay. Let's say these are all binary. Then it's basically saying 0, 0, 0, 1, 1, 1, all that 8 summation is what you need to do. Okay, that's one thing. So y is a generic assignment of these three random variables for this example.
And then similarly, what does y belongs to? What's any
This one?
of f?
Any is the neighborhood of f.
Okay,
Any means any is neighborhood. I should have explained it. So I can also use neighbor NBHT or something. So f is this node here. It has 4 neighbors. Okay, it's just saying find the neighbors y1, y2, y3, and x. So remove x. Okay, because you need to remove x because you're trying to create a message to x. Okay, if you're trying to create a message to x, you kind of remove x everywhere on the right hand side. Okay, because you're not supposed to average it out or anything. Okay, and that's it. So you remove x, and a neighborhood of f involves y1, y2, y3, So that's the three messages that you have. These three messages that you multiply them together. Okay, that's going to be some function of y1, y2, y3. This is the function of y1, y2, y3 and x, but x is fixed for each x. So you have some function of y1, y2, y3. You average them out for a given x. Okay. So now what did we do so far in the few minutes? We said initialization, we said variable node to factor node message, and we said factor node to a variable node message. Okay, two types of messages and initialization. Now what I want to show in this slide is that messages depend on all incoming messages, right? So what I want to show is that if you have a tree factor graph, there's a way to pass messages, couple of times, so that you can compute all sorts of marginal probabilities. Okay, in fact, at least all sorts of singleton marginal probabilities, and I'll tell you how to do that. Okay, so let's say you have a tree like this. It doesn't have to be this tree, any tree. Okay, any tree. Remember, a tree graph will have some leaves. Okay, leaves are the some extremal nodes where it's only where the degree of the node is just one. Okay, so for example, like you've seen binary trees, right, so far. So this type of a tree, these guys only have degree 1. Okay, those are leaves. Okay, and so let's say you have a tree. Okay, what you do is designate somebody as a root of the tree, because if you have a tree, other than the leaves, any node can be a root. Okay, let's say, for example, I can say this is the root, or I can say this is the root. If I say the second guy is a root, then it looks like an imbalanced tree, but it's a tree. Okay, designate somebody as a root, and then what you do is you start passing messages from leaves to the root. Okay, so in this case, I said the root is something else, some x3. Okay, actually you could have designated anybody as a root. Looks like. Yeah, in this case, I just designated anybody as a root. So in this case, I chose x3 as a root, and you pass messages from everybody else. If this is a root, then these two are the leaves, right? Leaves of the tree. You pass messages from here, and here there is no ambiguity, because if you're starting from here, these are here you start with initialization, because this guy is not connected to anybody else. So a message from this variable node to a factor node is all ones. Actually, we saw this 2 slides ago. Here to this is all ones. Okay, all ones. And then once I have passed a message from here to here, this guy, this factor node, to pass a message to this variable node has already an incoming message. So he doesn't have an issue. So he can compute the local function factor, incoming message is already present. So they can send a message from here to here. Similarly, this guy can send a message from here to here. Now this guy, if he wants to send a message to forward, okay, so we are all trying to send towards the root. To send this message, they already have two incoming messages. They just have to multiply them together, send a message forward. Okay. And similarly, all the way to the root. Okay. Now at the root, again, this guy being a root is also the leaf. So here the initialization is again, you can just use the initialization of all ones. Send a message here. Now this guy can send a message because it has an incoming message. It can send a computer message, outgoing message here. But the cool thing is, now at this point, this guy needs to send a message below. Okay, it has an incoming message here, and there is an incoming message computed here. Okay, so it has both incoming messages to compute a message this way as well. Okay, and similarly, this guy to compute a message to this guy has an incoming message. So what I'm trying to show from these two graphs is that for every node, any node you pick, it can send a message this way or this way. As in, it can send a message to all its neighbors with no issues, no chicken and egg problem. Okay. So no chicken and egg problem. Any node that you pick, let's say if you pick this node, x2, it can send a message to this factor node. It can send a message to this factor node because there's incoming message here and an incoming message there, right? And it can also send a message to this factor node because there's incoming message here and incoming message here, if it wants to. Okay. And so, okay. Yeah. And now, so let's say you did this. Okay. How much How much time does it take? Whatever the tree is, you do one pass of messages like this, which is completely valid. You can do this, and then reverse pass from the root to the leaves. Okay, so there are two passes that you did. Given those two passes, at any node, you can compute its marginal probability. Okay, so in fact, with those two passes, we can compute the marginal probability, which is the probability of just that random variable for each of the random variables in the tree in one go simultaneously. Okay, in the sense that you've done these message passes, right? One pass and reverse pass. Okay, once you did that, you can compute the marginal probability of x1, marginal probability of x2, marginal probability of x3, marginal probability of x4, all at the same time. Okay, there's no further computation needed. It's just a function of those messages. Okay, in particular, the marginal probability of x is going to be just the product of all the messages that it has received. Okay, that's a cool thing. And so marginal probability of x is just a neighborhood of x, all the factor nodes that it's connected to. Multiply the messages together from those factor nodes, and that's it. That's the marginal probability of x. So in one pass, or basically two passes, we have computed the marginal probability of 4 nodes. Okay, so that's like the efficiency gain. If you are doing variable elimination to find probability of x1, you would sum over everything else. To find the probability of x2, you would sum over everything else. Probability of x3, you would sum over everything else. So you'll do like four different operations. Okay, so here you're getting all marginal probabilities at the same time. No, I mean, so to do this, you need to designate some random node as a root node and send everything there and then reverse. Yeah.
But to marginalize, we don't need that.
No, it needs the messages from the factor nodes that it's connected to. In a sense, it's at this point it's not sending messages anymore. Whatever, let's say it's connected to 2 factor nodes or 3 factor nodes, it just has to multiply the messages from those 3. Okay. So for example, x2 has to multiply the 3 messages from these 3 guys. x4 has to just multiply, does not do any multiplication. Whatever message it got, it's a marginal. Same thing with this guy and this guy. Okay.
So you call something a root just for the sake of calling it root.
Yeah, just to
There's no special difference between the root and the leaf because you can take messages either.
You just have to designate something as a root so that you know, because it's a tree. If you randomly designate something as a root, you know at least one direction. So you know everything else is a leaf. So you know how to initialize and go forward towards the root and then back from the root. I mean, here I've designated the root to be the one of the terminal guys, but you don't have to. Okay. Yeah, you had a question.
We're looking at two marginal. I think I understand. We get the arrows going both ways from messages. We have all those.
Yeah.
Easily just pick one and do the product of everything going into it.
Yeah. So that way, I'm saying is actually just if once you pass these messages at every node, for example, this node, what is its task? It either has to pass message to this guy or pass message to this guy. Okay. I'm just saying that with these two passes, in this first pass, it knows what message to pass to this guy. In the second pass, it knows what message to pass to this guy. Okay. So every node knows what message it has to pass to its neighbors after these two runs. Okay. And once you know that, then if you just want to know marginals, whatever messages are coming in towards it, just multiply them together. That's my marginal probability. It's just a claim that I'm making here. Okay. We will not show it because it's basically just summations. Okay, so that's it. That's Wheelie propagation. It was like a pretty not complicated, but it's a mechanical thing, just like deseparation. Okay, but it can work on really large graphs. You don't have to think too much about it. As long as the graph is a tree, you just have to figure out, designate something as a root and just send messages, and it's very mechanical. And get back messages, and with that you get all the marginal probabilities. Okay, and not just marginal probabilities, you can also compute conditional probabilities and variations like that. What is it called, modes and so on, but we are not going to talk about that. Okay. So one comment before we take a break is that it is inexact for general factor graphs. General factor graphs means graphs which have cycles. Okay. Graphs. So we have seen our example did not have a cycle; it was a tree. Okay. And in fact, 2 slides ago also I was drawing a tree. If you have not a tree, then it's not clear how the messages propagate. Okay, there's some circularity in there. So, but you can apply Billy propagation, except that it's not clear what it's going to converge to. Okay, whether the numbers are actually marginal probabilities or not is not clear. Okay.
Are all DAGs also trees? Or do you think that's not true?
So if you had a DAG, okay, like this, okay, so node.
Okay, there's more than one way to get from A to C. So
Yeah,
it's
this is not a tree. It's not a tree. Yeah,
Okay. And so how would belief propagation perform?
would not work.
Okay.
You don't go with one of those zeros, just directly or matter with propagation, you still just go your root and back and forth.
No, here it depends on the factorization, right? So if the factorization is A, B, C, D is probability of A given, in this case, probability of, oh, actually the factorization is there. So here we don't even have to, so the factorization is basically, the factor graph is basically C depends on B, C depends on B and D, right? So the factor would be B, D, and C. Now B depends on B's parent is A, so there's going to be a factor and A, and there's going to be a factor and D, and there's going to be a factor for A itself. Those are the four factors. Right? Basically, you just look at what is the node, who are its parents, and those three will be those parents, and the node itself will be connected by a factor node. That's all. Okay, so let's take a break until 8:15, or actually 8:20, and then resume.